Okay, so for section 3.5, we're going to be talking about rational functions. Specifically, their graphs, applications, and models. Now remember, whenever we hear the word rational, what rational means is fraction. So what we're going to be looking at here is a graph that looks something like a fraction like that. What if we had, maybe we'll call it f of x is just equal to x plus 1, and g of x is equal to x squared minus 1. For a rational function, I could combine those two. So the first one would just look like a regular line. The bottom one would look like a parabola that's moved down 1 unit. But for a rational function, we would actually be graphing a combination of the two. Excuse me. So we're going to have x plus 1 over x squared minus 1. And this graph's going to look not like a line and not like a parabola. This graph would actually look like this. So that's something you probably haven't seen yet. These dashed lines are called asymptotes. And what an asymptote is it's a line that a graph approaches. Sometimes they cross, but most of the times they just get really, really close. We have a vertical asymptote that goes up and down, and we have a horizontal asymptote that goes left and right. Horizontal asymptotes, remember, are y, and vertical asymptotes would be x equals. These curved lines are called branches. So let's get into how to graph them. In our first exercise, we're just going to be modifying parent graphs. So if we had something like this, let's label this parent graphs. And let's say we had f of x is equal to 1 over x. The name of this is called the reciprocal function. And this graph looks something like this. We have a vertical asymptote along the y-axis. So that means the vertical asymptote would have the equation x equals 0. We have a horizontal asymptote. Horizontal asymptote has the equation y equals 0. And in general, this graph we're in the lower left and upper right. And you could see that if you plug in different positive x values, the whole fraction would be positive. Negative x values would give you negative y values. And of course, we have a branch here, and we have a branch here. What if we had this? F of x is equal to 1 over x squared. This doesn't have a name per se, but we still have a vertical asymptote along the y-axis. So we'll say x equals 0 is our vertical asymptote. The horizontal asymptote, we'll talk about how to find those later on, but in general, your parent graph for this just has y equals 0. And if you plug in any x, you'd get a positive y value. So instead of being lower left, upper right, you actually have branches. Both of the branches are above the x-axis. So what we're going to do next is let's sketch graphs based off of their parents. Sketch graphs based off of their parents, or let's say their parent graph, and state their domain. let's say we had f of x is equal to negative 1 over x plus 1. Now, the parent graph would be 1 over x, but we have this change and we have this change. This change is going to move the graph left 1 because it's on the inside. And the negative up here is going to reflect over the x-axis. So this graph would look something like this. Here's your normal graph, bottom, upper right. If we reflect it over the x-axis, it'll look like this. So that's a reflection over the x-axis. And then we're going to have to move the whole thing 1 unit to the left. So let me see if I could do that with my computer here. I'm going to try to just grab the branches. I'm going to move them to the left. Having a little bit of trouble just grabbing the branches. I think that'll do it right there. And we're going to move that to the left 1 unit like that. So you can see our new vertical asymptote would be x is equal to negative 1. But our horizontal asymptote doesn't change. Our horizontal asymptote would still just be right here. And that's y equals 0. We'll do one more, and then I'll show you how to do this step by step. What if we said f of x is equal to 1 over x plus 2 squared, and then minus 1? So we have a change here. We're going to go to the left 2 because we have 2 on the inside of the function, and then down 1. So this is what the parent graph looks like. And what we're going to do with this is I'll just grab the branches, and we're going to move them to the left 2, 1. All right, so this is the original, 1, 2, and then down 1, like that. So our vertical asymptote, instead of being at 0, is now going to be at negative 2. And our horizontal asymptote that was at 0, if we move it down 1, now the horizontal asymptote is going to be y is equal to negative 1. That's how we do that. So let me show you the general rules to graph these, and then we'll graph maybe 4 problems. So graphing rational functions. And these are going to be our 4 steps. So let's do it maybe looking at an example. So let's say the example looks something like this. Let's say f of x is equal to 1 over like x plus 2. All right, that's pretty easy to get started. First step we're going to do is we're going to factor completely. Sometimes when we factor, if we get cancellations, that's going to look like holes on the graph. So there's nothing to factor here, so we'll go to step 2. Step 2 is we find our vertical asymptotes. I'll put S in parentheses. Sometimes you can get more than 1, sometimes it's just 1, but the way that we get our vertical asymptotes is we set the denominator equal to 0, and we solve. So for our example here, the denominator is x plus 2. I'm going to set that equal to 0 and solve it. X is negative 2 is our vertical asymptote. For our third step, we're going to find the horizontal asymptote. for our horizontal asymptote, we have to compare the degrees of the numerator. We'll use an n for the degree of the numerator, and the degree of the denominator. We'll use a d for that. Okay, now if we're comparing two numbers, there's three different options. One, the top power could be smaller. The top power could be equal to the bottom. And the third option is the top power could be bigger than the bottom. So if the top degree is smaller than the bottom degree, like say if you had x plus 1 over x squared plus 3 or something, you see how the top power is 1, the bottom's 2? In this case, your horizontal asymptote is just y equals 0. But if they're equal, like let's say you have 2x plus 1 over x minus 1, see how the powers are equal? Then your horizontal asymptote would just be y is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. In this case, it would just be y equals 2 over 1. In this third case, we'll see an example with this. But if the top power is bigger, like if we had x to the second plus 1 over x minus 2, see how the top power is bigger, then there's no horizontal asymptote. We have to perform long division to find a slant asymptote. And I'll show you how to do this in an example later on. So let's go back to our original problem. It's 1 over x plus 2. So the vertical asymptote's negative 2, so I'll start graphing it. Negative 2 is our vertical asymptote. And a horizontal asymptote, well, the top degree, there's no x, right? So the top power is 0, the bottom power is 1. The top power is smaller than the bottom. So that would mean y equals 0. That's our horizontal asymptote. And the asymptotes are more just like scaffolding. They're going to give our graph shape. So the only other thing we have to find now is we have to find the branches. The way we find the branches is we plug in x values to the left and right of each vertical asymptote. So watch. I'll use a different color. Maybe I'll use green. The vertical asymptote's negative 2. So the next value to the left would be negative 3. The next value to the right would be negative 1. We're going to plug those in and see what we get. When x is negative 3, the y value would be 1 over negative 1. So the point negative 3, negative 1 is on the graph. On the right side, if we plug in negative 1, we get y is equal to 1 over 1, or negative 1, 1. Now remember, the graph approaches the asymptotes. So if we approach this and approach this, that's how we get our branches. Sometimes we could have 2 vertical asymptotes or more. but the rules are still the same. We're going to test x values to the left and right of every single vertical asymptote. So let's take a look at the 4 examples I told you we'd go through. And we'll follow those rules. Those rules could also be found in the supplemental materials section if you just want to print out kind of like a step-by-step guide. So let's take a look. First graph I wanted to do is, let's say, f of x is equal to x minus 1 over x squared plus 3x minus 4. Our first step is we have to factor. So the bottom factors down to be x plus 4 times x minus 1. And actually, you see how the x minus 1's cancel? If you're left with nothing, you just write 1 there, and we just get 1 over x plus 4. But we said in the notes when you factor, if there's a cancellation, like we canceled out x minus 1, we set that equal to 0, and that means that at x equals 1, there's going to be a hole on the graph. We'll see that when we graph it in a little bit. But now going forward, we're just going to look at our simplified equation when we go to graph. Our second step is our vertical asymptote. We're going to set the denominator equal to 0. So we get x is negative 4. We can start graphing this. And let's do our horizontal asymptote. It looks like the top power is, there's no x. Bottom power is 1. So if the top power is smaller, that means y equals 0. Is your horizontal asymptote. And now let's find the branches. I use green for that, and if it simplifies, you always want to use the simplified equation. So to the left, we could use negative 5. To the right, we could use negative 3. We'll plug those in. 1 over negative 1 would say that there's a point on the graph on negative 5, negative 1, which is right here. Approach the asymptotes. That's your branch. And if you use negative 3, you get y is equal to 1 over 1. So negative 3, 1's on the graph. Approach the asymptotes. That's what the graph looks like. Okay, so we have 3 more. What about this one? So we had f of x is equal to x squared minus 4 divided by x plus 2. First step is we're going to factor. And the top is a difference of perfect squares, so x plus 2 times x minus 2 divided by x plus 2. Well, those cancel, so we're going to get a hole on the graph when x plus 2 is 0 or x is negative 2, which reminds me, I think I forgot that on the last one. So let's go back to the graph. We said that there was supposed to be a hole when x was equal to 1, so I'm going to go to when x is 1 right here, and I'm going to put a circle on the graph, which means that technically there's no value at 1, because what that would do is that would give us a divide by 0 error. So just make sure you're careful. If you say that there's a hole, make sure you put a hole on the graph. In this case, we do have a hole at negative 2. And actually, we're just left with x minus 2. I mean, x minus 2 over 1, right? Well, that's not a rational function anymore. That's a linear function whose y-intercept is negative 2. And then we're going to go up 1 over 1. That's what the graph looks like. There's no vertical asymptote. There's no denominator. But we do have a hole when x is negative 2. So I'm going to go to negative 2 and go down to the graph there. And we're going to put a circle there. We can't let x be negative 2 because that would give us a divide by 0 error. That's it. That's all the graph is. You only have asymptotes and branches if you wind up keeping the x in the denominator. So 2 more. What if we had f of x is equal to 1 over x squared minus 9? Now if we go to factor this, you get f of x is equal to 1 over x plus 3 times x minus 3. So I mean, factoring is good, but it didn't simplify anything, but you should always check. Let me see if I could just move this over. I should have wrote factor here for our first step. So we factored and nothing canceled, so we don't have to worry about any kind of holes. So now let's go to step 2. To get our vertical asymptote, we're going to make our denominator equal to 0. Bring the 9 over. Take the square root. This would be absolute value. And we get x is equal to plus or minus 3. So this is new for us. We have 2 vertical asymptotes. There's a song. It's old though. It's called 2 is better than 1. It's kind of like a romantic song, but anyway. 2 vertical asymptotes aren't necessarily better than 1. It's just a little bit more work, but we'll figure it out. So 1 vertical asymptote's at 3, and 1 is at -3. Everything else is the same. So for our horizontal asymptote, there's no x on top, so the top power is 0, and the denominator power is 2. The top is smaller, so this means that our horizontal asymptote is just going to be y is equal to 0. And now let's find our branches. Now because we do have an extra vertical asymptote, that's just one more number we're going to have to test. But I'm going to plug in to the left and to the right, just like we usually do. To the left and to the right, just like we usually do. So we're really just plugging in a couple more numbers, but let's plug those in and see what our points look like. If you plug in -4, you get y is equal to 1 over 16 minus 9, or 1 over 7. So the point -4, 1/7 is on the line. 1/7 is above 0, so I'm going to put it above the horizontal asymptote. If I plug in -2, we get y is equal to 1 over 4 minus 9 is -5. So we have -2, -1/5, which is below the horizontal asymptote. Put it right there. We plug 2 in, we get y is equal to 1 over 4 minus 9 is -5. So we get 2, -1/5. Then if we plug in 4, get 1 over 16 minus 9 is 7. So those are our points. Now in the middle, we have an interesting situation. If there's 2 vertical asymptotes, you could have 4 options. So if you have a problem like ours, where you have 2 points that are both underneath, they connect and form a parabola. If you have 2 points that are both above, they connect and form a parabola. If you have one above and one below, they connect to form like a cubic function. And one below and one above, they connect to form a cubic function. So it's only in the middle do they ever cross. But in this case, they're not going to cross. It's just going to approach the asymptotes like that and look like a parabola. The outsides are like normal. They just ride up against the asymptotes. And that's what it looks like. All right, and we'll do one more problem. What if we had f of x was equal to 3x squared minus 4 over x minus 1? First step is we try to factor. Nothing factors, so we go to step 2. Step 2 is our vertical asymptote. we set our denominator equal to 0, and we get x is 1, so we could start drawing this. Okay, the third step, this one's a little bit different. The top power is 2, the bottom power is 1. So we're going to have to do long division here. We'll divide x minus 1 into 3x squared plus 0x minus 4. Remember, whenever you do division, if you're missing the term, you have to put 0 in for that. X times 3x gives us 3x squared. 3x times negative 1 is negative 3x. Remember, we're going to subtract these. And then x times 3 gives us 3x. 3 times negative 1 is negative 3. And if we subtract those, we get a remainder of negative 1. When we're doing this kind of process, we don't care about the remainder when we go to graph rational functions. This is our slant asymptote. So our slant asymptote is going to be y equals 3x plus 3. So let's draw that. We're going to go up 3, and then up 3 over 1. And that's going to give us what's called a slant asymptote. Now, it's just like any other asymptote. The graph's going to get close there. So let's finish this up by finding points to the left and right of our vertical asymptote. Like we could use 0 and we could use 2. Let's plug them in and see what they come out as. If we were to plug in 0, we get negative 4 over negative 1, or 4. So that means the point 0, 4 is on our graph, which is right here. It's going to get close to the vertical asymptote, and it's going to get close to our slant asymptote, so just kind of right up there. If we were to plug in 2, we'd get 3 times 4 is 12 minus 4 is 8 over 1. So then when we go to graph the point 2, 8, let's go to 2, like over here, and 2, 8, 1, 2, 3, 4, 5, 6, 7, 8. It's going to be like really close to the asymptote, but it's going to be right there. So if we have to get close to the slant asymptote and close to the vertical asymptote, that's how the graph's going to look.